All right, so in the last video, we went ahead and derived a partial differential equation that describes how this die moves within the bar. I want to highlight
bar.
within this hollow bar, also known as a pipe. Thank you, Rahana. If I say bar one more time, I'll have to buy you a drink. But the point I want to make right now is that this partial differential equation is not actually sufficient to really describe what goes on in the system. And the reason it's not sufficient is that there's nothing embedded here about where the die is initially. There's nothing embedded about the fact that this actually is a hollow bar that has fixed ends. So we really need to make to add some additional vocabulary to our quiver in order to be able to deal with this. Mm-hmm. And the way that I'd like to add that additional vocabulary, and you can please correct me when I do something stupid, Rahana, is to make a connection between some things that you did in linearity and things that you have to do with PDEs. So let's first remember back in linearity, we're dealing with ordinary differential equations, right? So for example, you might have had the differential equation x dot is equal to a times x, right? Mm-hmm. And with that differential equation, you were able to come up with general solutions, right? So the general solution for this differential equation is what?
Now you're asking me to integrate.
I am, or if you were a physicist, I'd be asking you to look at it and say, oh, it must be an exponential, which is what I would do. But you certainly could integrate it. You get the log natural and so on and so forth. The function whose derivative is proportional to itself. So I end up getting x is equal to some arbitrary constant times e to the a times x. Right? And this arbitrary constant comes from the fact that I have to do that integration, right? Mm-hmm. So it sort of comes from the arbitrary integration constant. Yeah. Now, you remember that with ODEs, this actually is not one solution. This is an infinite number of solutions because I can choose any value of A that I want to, right?
So how would we find which A works?
Well, I think that in linearity 1, the way that was thought about is by solving initial value problems. And this should be to the t, not to the x, sorry. Mm-hmm. So if you're sort of given two things, you need to be given what the derivative is, and you've got to be given what the initial value of x is, right? So let's say it's x naught, right? If you're given those two pieces of information, then you have enough information to actually find the particular solution to the problem. Right? Mm-hmm. And this now actually doesn't have any arbitrary constants in it. This tells you how the function x varies in time, and you're completely done.
Because when we plug in t equals 0 in that general solution, we get a equals x naught.
The way we took this, we took this initial value and made sense of it, is we said, okay, it's got to be the case that x of 0 is equal to x naught. So when I plug 0 in here, a times e to the 0 is 1 is equal to x naught. So therefore, a must be x naught.
Great.
Right? Okay, so that's what you did back in linearity 1. And there's actually something that's pretty analogous when you talk about solving partial differential equations, but there's a little bit more going on. And the reason there's a little bit more going on is you have a lot of different derivatives running around in these partial differential equations. Right? And you have a function that depends on multiple variables. So let's write down we were dealing with this partial differential equation. So this first derivative, the first partial of psi with respect to time is equal to a diffusion constant times the second partial of psi with respect to position.
Right.
Now, one of the things that we probably need to do is actually something very analogous to initial value, right? Which is we need to introduce the idea of initial conditions.
Does that mean time 0 again?
Right. That's very analogous to initial value. It's asking the question, what are the conditions at time equals 0?
Okay.
So this is asking the question at t equals 0, what does psi look like? Okay. Mm-hmm. And notice the answer to that question is not just a number, it's actually a function, right? You're actually finding a function of t equals 0.
A function of x?
But x, right? It is still a function of x. And so if I actually plotted that for this bar case, right? So here's x equals L, x equals 0, and if I plotted psi, right? Initially, I've got this high concentration of psi in the middle, and then psi is 0 elsewhere, right?
So let me see if I understand this. This is like if I have a time series for psi and I take one snapshot right at the beginning.
That's right. This is the first snapshot.
And then
exactly.
It evolves over time.
Yeah, one thing you might note is the actual connection between this and systems of linear differential equations, right? If I had, instead of a single differential equation, right, I actually had a system of differential equations. So x dot is equal to a times x, where a is some matrix, right? In this case, you end up getting a solution, right? That's a sum with arbitrary constants of the different eigenvectors times their times e to the relevant eigenvalues. So let's make those all i's, and then we go I equals 1 to n, where n is the dimensionality of the problem. And so in this case, you actually sort of match up what the weighting is of each of these. So there are sort of multiple initial values that you need to choose, one initial value for each element in the matrix, or for each element in the vector x. And so here you could sort of think of psi as being sort of an infinite dimensional matrix, and we're choosing a value for each of the initial each of the initial elements in that matrix.
Sure.
Does that connection sort of seem sensible? And I haven't violated any math laws by saying that?
I think math will survive.
Okay, all right. So that's one thing that we need to deal with is initial conditions. That's an important term you should be taking away from this video. And that is very analogous to initial value. But there's actually something else that's really important here, which is that we don't just have a derivative in time to deal with. And you remember the derivative in time here is what gave us this sort of arbitrary constant, which required an initial value. We also have these spatial derivatives. And those spatial derivatives are associated with the fact that this physical problem has some spatial characteristics, right? If we go back to the physical problem, what's actually happening at the ends? Well, at this end, the die can't go anywhere at this
x
end,
equals 0.
right? Once the die gets to x equals 0, it's not allowed to go anywhere. In other words, there can't be any flux through this surface, right? And there also can't be any flux through this surface. And so that actually imposes two other conditions. And if we actually go back and we look at the sort of flux expression, so remember that the flux due to diffusion is the negative of the diffusion constant times the first partial with respect to position.
Yes.
Right? This says that when the concentration is changing in space, then I get a flux, because if I have higher concentration to lower concentration, the stuff at higher concentration wants to travel to the stuff at lower concentration. If I don't have a spatial derivative, then I don't have any flux. Right? Well, because of the fact that the bar has closed ends, it must be the case that the flux at x equals 0 must be 0.
And also at x equals
and also
L, right?
at x equals L, it must be 0. Right? And if I rewrite that in terms of psi, this implies that the derivative of psi at x equals 0 for all times, right, has to be 0. And the partial of psi with respect to position, with respect to time at x equals L for all times has to be 0. Right? So I have two additional conditions on psi, right? I don't just have the condition of what psi looks like at time equals 0, which is my initial condition. I also have conditions that are at sort of the physical edges of the problem. Right?
Should that be with respect to time?
No, this should be with respect to position.
Okay.
And it should be true for all times. Because this is saying that the diffusion current is 0 at the edges.
Okay.
Okay? Does that make sense?
Then I misheard you. Okay.
I probably said time at some point, and I really apologize. But what I have written down here, unless I'm on drugs, is actually right. So if we look at this, this is a new kind of condition, and it's one that you probably haven't seen as much before. This is what's called a boundary condition, or a set of boundary conditions. And when you're solving a partial differential equation, you need to not only have what the condition is at the beginning of the problem, at time equals 0, which is the initial conditions, you also have to have conditions that apply at the boundaries of the problem so that you know what's going on at the edges.
So here's what I'm wondering, Mark. For the time constraint, We just needed to know the value at the initial time,
Mhm.
t equals 0.
That's right.
So why do we need the boundary conditions at the beginning and the end of the pipe? Why can't we just say this is what we have at x equals 0?
Well, I think there might be two answers to that. And I'm going to give a physics answer to that, and then
Okay.
maybe I'll ask you for more of a math answer, because I think there's a good math answer for that too. But the physics answer for that is, look, you've got a physical situation here, right? You have this pipe, and I'm not allowed to have any current here, and I'm not allowed to have any current here, right? I'm not allowed to have, there can be no diffusion across this surface, there can be no diffusion across this surface, because this is the part where the bar is solid instead of having a hole in it, right? So physically, this should be true of the concentration at those points, because physically I can't have any diffusion current at those points.
And physically, those are what's happening at the two ends. They're independent of each other, so we could have maybe a different problem where you're not closed at one
Oh
end.
yeah, that's a great point. I could certainly imagine that instead of having this be fixed at the end, maybe I'd have this be open going off to infinity. Right?
And
So maybe my
it's-
pipe is just
Sure.
fixed at one end. At which point I probably would have to think about a different boundary condition here. And now we might be getting into more of the math issue. Like let's say that I made this pipe go off to infinity. Well, how would that change these boundary conditions? Well, it still would be the case that I couldn't have any diffusion at the left-hand side, right? So this would still be true. But the right-hand side is actually off at infinity. And since the right-hand side is off at infinity, I think my boundary condition at infinity would actually be that psi is equal to 0 at
Because you
infinity.
taper off
that
eventually.
if psi is non-zero at infinity, what that says is that I've got an infinite amount of dye in the system, right? So my
Right.
total amount of dye has to be fixed, so it's got to go to 0 there. But that's a physics answer, and I think there's a math answer about why there are two of these.
So the way I was thinking about it is, can we see the equation again, the differential equation
Yeah.
again?
So where's a nice version of that? Here's a pretty nice version of that. Right. So here's our
So-
different partial differential equation.
These constants,
Mm-hmm.
thinking as math, I'm thinking in order to solve for this piece of the equation, it's a second order differential term in terms of x, so
Mhm.
we'd have to integrate twice. So I was wondering, every time you integrate,
Oh yeah,
to
that's right. When
solve
you
for
when you integrate, each time you integrate,
Like
you
you
pick up
did for the
a
ODE.
constant. And so with the ODE, since it was a first order differential equation with the ODE,
Exactly.
we actually had a single condition to meet. If we had a second order differential equation for an ODE, we'd actually have two conditions to meet. Like for example, if I'm doing a sort of acceleration problem, I need to tell you both what the initial position is and what the initial velocity is, because I've got to integrate twice.
Right. And so, for instance, maybe if on the left-hand side we had a different equation, which was the second derivative with respect to time, we would probably need not just the initial time condition, but some other time condition as
Yeah,
well.
exactly.
Does
In
that
fact,
sound right?
that sounds absolutely right. And in fact, if you make the interesting little note here, if you make this left-hand side be d squared psi by dt squared, this turns into something very similar to the wave equation, which describes
That's right.
how say a membrane might vibrate. And if you think about a membrane, then the psi would end up corresponding to the height of the membrane. For a membrane vibrating, you would actually need to know both what the initial position of the membrane was and also how fast the membrane was moving at each point. So you'd actually need those two initial conditions from a physics perspective as well.
Great.
Isn't it great how math and physics just work together?
Isn't it amazing?
We better stop this video now.